And we are live. Okay. Just wanted to welcome everyone. We have some visitors from Dallas, Fort Worth. Very cool to see. We have two presentations tonight. We'll be starting with Richard Farr and his talk on Judy Arrays. So let's just get that screen share going. Entire screen share. You are screen sharing. All right. Can you guys see the first slide okay? Just checking, actually.
Anyone there?
Oh, yes, you can. Okay.
All right.
I was checking anything.
All right, take it away, Richard.
All right. Welcome. Finally, the weather's kind of cooperating for one of these things, so that's kind of nice. So today, my talk is on Judy Arrays. Just show of hands, how many people have actually heard of Judy Arrays before? A couple of you.
That's me, because I heard about it earlier than you.
Great. Yeah. So we'll go into what they are and what makes them kind of pretty interesting. So from the manual, Judy is a programming library that provides a simple interface for array-like storage of word or string indices. They're remarkably fast, space-efficient, and simple to use. They require no initialization, configuration, or tuning. Yet it also works over a wide range of data and billions of indices from sequential, clustered, periodic, random. So, pretty bold claim they've made. So in a traditional array, right, you have your consists of a continuous segment of elements that are indexed by some start location plus a memory offset. The benefit is very fast lookup, insertion, and deletion of any given index. The main disadvantage, though, is what if, for instance, you wanted to store 0 and you also wanted to store 2 to the 64 minus 1 in an array? How would you also efficiently iterate over the order, or over the sparse set, right? If you had an array with only 5 elements in it, how do you efficiently iterate over that? How also do you quickly get a count of the elements in the array? So some of these are some of the questions that traditional arrays don't really help with. So usually most people, what they do to solve this is they use a hash. Efficient lookup and insertion uses relatively little memory. The only thing is generally it requires you keep a separate index if you want to be able to do in-order traversal over the elements. Also, hash parameters and the hash function itself, depending on how much data you're talking about, they need to be carefully selected. Otherwise, you start getting a lot of collisions. Generally, what happens with a lot of this, when this happens, is you can always reallocate the hash, increase the size of it. But this generally is pretty costly to do. You have to basically copy the entire data structure, and it introduces unpredictable latency into your operations because you never really know when it's going to get full. So a little primer on digital trees. So a simple flat array requires the entire expanse's size in memory usage. But what if we use more than one array to look up the index? So for instance, simple ideas: divide our original array in half and decode the index in steps. So take the first half of the index, let's say the first 16 bytes, and look up a pointer in the array, and look it up in the first array, and it will give you a pointer to the second array. And then take the second half and look it up for the final value in the second array. So if the population is sparse, then likely most of the pointers in the first array will just be null pointers, so we won't have to allocate all of the second arrays. So we save quite a bit of memory. And this basic data structure of multiple levels with multiple fan-outs from each is known as a digital tree or a trie. And here's just a simple example. So decoding 485. In our first array, we go from a root pointer, we offset at 4. We get another pointer to the second one, offset that at 8, pointer to the third one, offset at 5, and then it points to the actual data that we're interested in. So very simple. The order of a digital tree is the number of branches that can be taken at any level. A low order wastes less memory because fewer entries in each branch are going to be null pointers. On the other hand, how a low order tree is deeper, there's going to be more levels, so it's going to require more indirections to decode the key. If we could somehow combine a high order tree but with low memory waste. So that's what Judy tries to do. Judy uses order 256 branches for performance, which means that in a 32-bit expanse, it's about maximum of 4 lookups that would be required to get to any entry. If this was just a vanilla try, though, this would waste a huge amount of memory, and it wouldn't be performant. So Judy uses a variety of what they call tricks in order to compress the size of each branch or leaf, depending upon how full it is. So there's 4 different flavors of Judy arrays for different types of data. You have the Judy 1, which basically just maps your key, a fixed size key of size t, to a binary true-false. Judy L maps essentially a size t to a size t, so to an int. HS maps variable size strings to an int, basically, or a pointer. And then Judy SL maps null terminated strings. This one isn't used as much anymore, but it's still there. One of the things that Judy also keeps in mind is CPU cache lines. So in a real machine, the main memory access is painfully slow compared to the CPU, which is why memory is loaded into the CPU cache. The amount of memory read and cached at a time is typically about 16 machine words long. Depends on the architecture, but the x86, that's typically what it is. So algorithms that want to be fast must be cache aware and designed from the ground up to efficiently make use of the CPU cache. You can have a very beautiful algorithm on paper, but in implementation it could be pretty slow. So here's an example of the cache fills that would be required for an order, a digital trees order. So with a flat array, it's simple. There's no indirection. There's just one cache fill that would be required to load in whatever area of memory you need. With Judy, with the 256, it requires 4 indirections, 4 cache fills at most. And then if you have 16, it's 8, and so on. For a standard binary tree, in order, it would require 32. So that would be pretty slow if you were using just a standard binary tree to look up all this data. So in this talk, we'll mostly just talk about Judy 1 and Judy L. The other ones are kind of more complicated, and they build upon this. These are complicated enough, so they get the gist of it. So there's these are the array internals, or the data structures that the Judy array uses. There's the array pointer, the root leaves. There's a population or memory node, the JPM. There is a pointer, or sorry, that's supposed to be a Judy pointer, which is a special pointer, a fat pointer. There's branches, and then there's leaves. So the array pointer is basically just the root pointer to the entire Judy array, just like a typical one-word pointer that you'd have like in C. One thing that Judy does, though, is because it always is referencing 2-word aligned objects, they can basically use the least 3 significant bits, because they're always going to be 0, to encode the object type for free. So Judy actually, even just with this simple pointer, it can store up to 3 bits, and sometimes 4 bits of information. So what they use this for is to optimize for the case where there's only 1 or 2 indices in the entire array. Doesn't sound like much, but it's actually pretty useful if you're using, let's say, like a huge number of these arrays, if you have like an array of Judy arrays. So there's a good way of efficiently, compactly storing that there's like maybe only 1 or 2 things in here. So it's pretty basic. You just have your 32 or 64-bit word. In this talk, we'll mostly be talking about 32, but most of these apply to 64. There's a few differences. But yeah, the address takes up 29 bits, and then they encode the type in its low order 3 bits. So then we have what's known as a root leaf. So if a population is small enough, then Judy can basically store all the entries in a single root leaf. This leaf is limited to 2 words, machine words in length, for Judy 1, and for 4 words for Judy L. So here's an example of a Judy 1 root leaf. You have basically the root pointer, which points to the leaf, and the leaf stores in the first slot has the population, so the number of entries, and then you have I, which is the index. And then you have another example where you have 3 indices, and then 4, and up to 31 in a root leaf. One interesting thing about Judy is it only gives you memory in certain sizes. So in the third example here, you can see there's an empty space. That's because it actually only allocates. So you can't get 5 words. You have to allocate 6. And with Judy L, it's very similar, except that you also have values that need to be stored, not just the index, but the value. So the indices are still first, and then what you do is you have the values packed afterwards. So this is why it's basically double the size of a standard Judy 1. So that's the simple case where there's very few elements. And they're only used when, what happens is when there's more than 31 indices, a JPM will be used instead. So Judy will internally replace the root leaf whenever you insert more than 31. And a JPM is 10 words in size, and it's basically a header that just includes the total population, counter, pointers into the data structure, as well as some other information. So here's basically what it looks like. You have total population. You have the top Judy pointer, which takes up 2 words. You have the last index. It's just an optimization, so it knows what the last index is. the last Judy pointer, which points to the last one as well, so that you could easily traverse backwards. Value to return is there so that you don't have to, when you're recursing, you don't have to pass in an additional data structure to store the return. You just shove it in there, and then after the tail recursion, you can just grab it from there. So that's an optimization. And then there's just some miscellaneous error codes and memory information. So now we go on to Judy pointers. So they can point to various classes of children nodes. Null, so there's nothing. A branch, a leaf. There's a thing, an optimization called immediate indices, and there's also a full population, which is for Judy 1 only. So a Judy pointer is always 2 words in size, and basically can be thought of as a 2-element array. For the standard case of null, branches, or leaves, the first word is a standard pointer to the next child, and the second word encodes the pointer type as well as the bytes decoded so far and the population count of the sub-expanse that's still underneath. So here's an example. We have a standard pointer, and then the second word, we have the decode bytes and the population bytes. And what's interesting about this is as you go lower in the tree, the decode bytes will increase in size, and the population decreases correspondingly because there's less number of elements that could be possibly under. So these actually, this will move. In each level of the tree, there'll be, in the first level, you'll have just 1 decode byte, and then you'll have 3 bytes for the population, or sorry, 7 bytes, and then it moves as you go down. So it's pretty nifty how they put it in there. There's an optimization as well with Judy pointers. So instead of pointing just to like a branch or a leaf where the actual data might be, they actually in some cases say, hey, if there's a few of them enough, we can just put them in the Judy pointer itself, right? Save the lookup. So when the sub-expanse is really small, instead of a further indirection, the values are essentially immediately packed into the pointer itself. And in the case of Judy L, they then also use a separate value-only leaf that stores the values. So this would be what it would look like, different examples. So for Judy 1, you'd pack the first index here. Let's say that you had 2 indices that were 1 by each, because it depends on where you are in the tree how big these indices are going to be still. Then you could pack them here. Here you can pack up to 7. So you can pack them all in different ways. In the case of value ones, you basically can store the value here, or in some cases, if there's not enough, you have a pointer to a values-only leaf. So this is just kind of a hack or optimization that, again, reduces the number of lookups, which is the name of the game for performance. So where are we at so far? We have array pointer, which points either to a root leaf or a JPM. The root leaves allow a small number of items to be accessed directly. Once the array grows large enough, the root leaf will be replaced. And the JPM contains the array metadata and points to the first Judy pointer, which is basically a fat pointer that points either to a branch or a leaf, which we haven't talked about yet, and if there are few enough items, directly encodes them into the pointer. Thought this quote was kind of interesting. What we're talking about here. So now we go into the branches. So how do we compress these branches? So there's 3 possible strategies to use for branches. There's linear, when you have a relatively sparse population. There's a bitmap for a typical population, and when it's dense, you just use an uncompressed array, like a basic array with no pointers. So linear branch is only 16 words long, used when the population is basically up to 7 or smaller. And along with a count, it stores the sorted list of sub-expanses within it, and it also stores a list of Judy pointers to the next branch or leaf, depending on whatever the case may be. So here's an example of a branch. So you have your Judy pointer that points to it. Here you have your population count, and then you have your indices that are in this sub-expanse, and then you have the pointer to the next expanse that's after that. So this is essentially, and the way you would access this is just through linear search, basically. Now, if you have a bigger population, you use a bitmap branch. So, and the way this works is there's actually 2 tiers. There's the bitmap itself, and then there's subarrays which hold the actual data. So the bitmap is always 32 bytes long, and basically contains 8 bitmap sub-expanses within it, as well as 8 pointers to the subarray. And the subarray itself consists of a packed list of Judy pointers, 1 for each bit that's set in the parent bitmap. So it kind of looks like something like this. In this example, this bitmap here, there's nothing set, so this is all null. In this example here, we have some bits set. So this next subarray pointer here actually has some values. It points into this array. And using the bits that are set here, you can then look up which value corresponds with which bit. The reason the 2 tiers are used is to keep the size of the bitmap small enough so that it will fit within 16 words for efficient inserts and deletes. So if this was larger, then this would fit. This fits in one cache line right now. So it's very efficient to search through and insert and delete things with this. If it was bigger, it would be a problem. The pointers and the subarrays are interspersed as well. Originally they weren't, but they changed it later. The idea being that on machines that only have 8-word line caches, it reduces the number of fills that they potentially have to do. If they were afterwards, then they would always have to read all of the indices first before they could get into any of the values. So by interspersing them, the idea is to make performance better for crappier machines, basically. And finally, the uncompressed branch was pretty simple. It's basically just an array. It has the value in there and null pointers where they're not. So now that we finished with the branches, it's on to the leaves. So leaf compressing strategies, there's basically two: linear for sparse populations and bitmap for medium and dense. And they didn't use uncompressed because they said actually in the end it doesn't matter. Bitmap still saves memory and time over using uncompressed for leaves. So linear leaf is pretty straightforward, just a packed array of the indices in sorted order again, and basically contains only the minimum number of bytes remaining to be decoded at the leaf, at the level of the leaf. Judy L also has like a separate value area. There's one word for each index. So here's like an example of Judy 1 leaves. So you have your pointer into here. You have your indices. For Judy 1, there's no values, just whether it's true or false. And Judy L, in addition to that, you also have the values that are stored. And for a bitmap, basically when there's only a single byte left to decode, and there's a sufficient population, it saves memory just to represent each index as a bit in this 256 bitmap. And again, subarrays are interspersed with the bitmap entries, so it looks basically something like this. For Judy 1 and Judy L similarly, you have subarrays that these point off to look up the values. So when do you use Judy? So we've gone through the infrastructure of it, the internals. Basically, if you have large, sparse data sets, unpredictable data, both in density and pattern, and Judy does work better on semi-sequential data rather than pure random, but it still can handle both. And you also want a relatively predictable operations with low latency. So here's an example I got. This person wrote or did a benchmark between hash maps and Judy arrays. So what's interesting you can see here is the hash maps are the ones that are going all up and down, and that again.
The axes?
So the axes, this is number of elements down here, and this is the time that it took. So you can see, the hash tables basically you have an unpredictable latency. This is when basically the hash table gets full and it's reallocating. So you have this kind of sawtooth pattern. Whereas down here, for instance, you have this is Judy with sequential data. So it's very performant. And the only thing is, yeah, with Judy with completely random data, is there's this potentially an issue here when you reach about 1 million elements. Again, though, I don't know if you continue going, if this would continue growing. It's hard to say. But you can see kind of that you have a more predictable latency with Judy, and that it performs reasonably well on sequential data as well as on somewhat sequential data. So in terms of memory usage, we have, again, Judy is very low on the scale and very consistent. And again, you have a lot of going all over the place with some of these hashes. So again, so that's probably the hash is reallocating.
I mean, for Judy.
Oh, here?
Yeah.
That probably has to do with because it would probably be that it reached a point where it has to start. So you'd have a root leaf, then you'd have a JPM, and then after that, you're doing some kind of allocation probably to do like maybe more branches or something. I'm not sure.
Going into more components.
Yeah.
You have to go from just a root leaf, just a root node to more Judies.
Maybe, but the root's only at 31, so I'm surprised that it would be up to 1,000. But
Well, that's 1,000 elements.
yeah, right here, 1,000. So there's obviously something that's going on, and it could be an implementation detail. It seems interesting because it's like it's up and then it goes back down to where it was before. So it could be even a bug. Who knows? In the library. Yeah.
So, change some kind of change strategy and has 10 bits.
Mm-hmm. So the implementation. So first of all, it was invented by Doug Baskin while working at Hewlett-Packard. He named it after his sister. If you're wondering where it came from, he couldn't think of anything better. So he's just like, yeah. The original implementation was written by a team of engineers at HP. 20,000 lines of C code, and it was released under the LGPL license.
Was it written in C or was it assembly?
Well, I think maybe parts of it were written in assembly, but it was mostly C and some assembly. Yeah. Basically, they tried to squeeze out every bit of performance. What's interesting as well is that actually more recently somebody else created an alternate implementation with only 1,250 lines of code. I haven't tested it, so I don't know if it stacks up in terms of performance, but that would be interesting to see if it was as good. So we can do now a quick Perl example of how to use it in Perl. So does this work? Yeah, okay. So I basically wrote this really simple program. Not necessarily the smartest way to do it, but just a little example. So first of all, yeah, so it is on CPAN. You can use just basically install the Judy package. There's an alien Judy. It's basically an access module. So this is basically a very thin wrapper around the C library. So these are some of the APIs you have. Like for instance, you have get and set. So this is Judy 1, which is just the bit one. So you have get and set, which basically sound like what they are. You have first and last, which basically you ask it what's the first element from this index or what's the last element from this index. Next and previous, which allow you to basically go forwards and backwards through the structure. And you can also get a count and the amount of memory that's being used by the structure. So this is just a simple program that you just give it 2 files and basically goes through, reads them, and just does a kind of a binary compare of them and adds the where they match, it adds it to the Judy array. The idea would be you might use this in the application where you wanted to find like a match inside of something. And then not only did you want to just print it out, but then you might want to manipulate it afterwards, do some operations on it. You see it's pretty simple to use. You just declare the Judy data structure, it's just undef, because in Judy a null pointer is actually technically a valid Judy array. So you just pass it into the set function, and you just say set this index, and it will just go and set that bit. So this basically just loads it up into the Judy array, and then I just wrote a couple of little things that just use some of the easiest things. So here's the count function. You give it again your array and your start and your end index. By default, if you pass in -1, it basically means the end. So this is just saying, give me a count of the entire array, how many elements are in it. But you could pass in any start or any end index that you wanted into here to get a count between those two. The memory used by the Judy data structure. Also get the first element here, the last element if you want. Here's a range, so if you want to iterate over it. So here I make it so that you can iterate both forward and backwards. So if you're going forwards, you get the first element in the Judy array, and then you basically just print it out, and then you just say called next, and you pass it wherever you currently are, and it will just give you the next one. And if it's not there, then it'll just return undefined. And then the reverse is very simple. Just use last instead and use previous to go backwards. So really simple, easy to use API. And test is just ask it, is this thing set? Is this bit set? So I can just show this off here. I just created basically 2 random files here, file 1, file 2. So now it's gone and it's loaded it in, and now I have this like really crappy REPL that I created. So you can like say summary, for instance. So the number of common bits in total between these two. So this was I think it was 10 megs or something. I can't remember how much it was, but that's how many common bits there were that were found. And currently Judy's using 160 kilobytes to store this. You could say what's the first element. But in this case it's 0. The last is that. You could do, let's say, a range. Let's say you wanted to know what are the elements between the bits that are common between 250 and 500. Print them all out. Also do reverse 900, let's say, down to 890, like that. And you could ask, is this bit set? That one is, kinds of things. So really simple API to use. This is the Judy 1. For Judy L, it would be very similar, except it'll also return to you the values that you set, which is basically a size T, so you can basically just use it to store a pointer, or basically anything else that you probably want to do. Yeah, any questions? Nothing at the moment too much. I've been toying around with, actually I've been toying around with writing a D language wrapper for this to make a nicer interface. I mean, this interface is okay, but it's still very C-like, very low level. At the moment, I have a couple ideas of things that might be useful for, like maybe something like an order book where you have potentially like a large number of prices that you might want to store. And there's no like real limit on, somebody could put an order in for like 1 million or something. It might be useful in that sense. So I've just been playing around with it, but I haven't used it for anything too much yet.
Good question. So it seems like that this is good for one-dimensional arrays. So how about for multi-dimensional arrays?
Yeah, that's it's very good for that as well because. Oh yeah. So the question was, this seems that it's good for a single-dimensional array. What about multi-dimensional arrays? Yeah, you could easily have arrays, Judy arrays of Judy arrays. Since each, I mean, obviously your lookup time is going to double in that case. But the nice thing is that, as I said, like a null pointer is basically considered a valid Judy array. So it's not. It's really easy just to declare a two-dimensional array that won't use too much memory out.
Does it allocate space as it goes along, or does it do rebalancing?
So it allocates as it goes. It doesn't rebalance, but it does do some optimizations where, like, if a certain node grows to a certain size, it will redo the type. So like it'll change from a linear to like a bitmap at some point, and it will eventually go from a bitmap to uncompressed. So there's a lot of logic that in terms of like when it's inserting and also when you're deleting. It uses all these heuristics to try to figure out what the optimal thing is. The nice thing is when it does rebalance, it's pretty predictable because it doesn't actually rebalance the whole tree like a lot of other algorithms have to do. It's just looking at the particular node where you insert. Is there some optimization that it could do to that? So it's pretty performance in that respect.
I have a question. It sounds like everything gets stored in sorted order. So when you pull stuff out, it comes out sorted. Yes.
Yes. Yeah. It is stored sorted.
It seems to me if you add something in the middle, it ends up going to a node that's already full. It's going to split that node too.
Well, there's not. I don't think a case that the middle could be full. I mean, it might just be that it gets fuller to the point where it's like, well, now I got to upgrade. Because remember, each sub-expanse is kind of defined. That there's only going to be this many elements at most that are going to be available, like for this index range. So there's no case where it actually ever gets full and has to split it into more nodes. It's just that it might have to upgrade.
No, what I'm saying is really neat because it's set out to rebalance the whole tree. It just takes one node and splits it into two, and then some in one and some in the other. This is the way
I don't think it splits. I think it just.
So it's already got virtual memory for every single possible location. So it never has to split anything.
Okay, so it just says, okay, now this guy is being used. Okay.
Yeah. So what's interesting about it is like there's some links I've posted here as well at the back end, but in the
screen share.
Okay, in the manual which I was reading through, they were like, yeah, what's nice about this is in theory it's relatively simple. It's just a digital tree, but there's all these hacks that they put in, and they call it's academically impure. So obviously academics would hate this data structure. Impure. It's too complicated. There's too many node types, too much going on. Their view was, engineering skill is more important than just a purely, elegant design. All right. I think that's it. Unless there's any other questions from the line, or. Yeah, you can click on it if you want. It's at Google Code. It's on Google Code, which means it will be on Google.
Which one? This one?
Last one. Let's see. Is there a way to easily just get to the source? Let's go to downloads, maybe.
You just post a link on your line.
Yeah, there we go. Go to 64. Whoa, that's a weird naming convention. Click it. See what happens.
This one?
I don't know. Yeah. Just to see it.
view raw.
Yeah, let's view it raw. Oh, weak.
I wonder if you have one.
Yeah. Good old Google code.
Open with one. And you can't see that at all.
Just scroll down. Yeah, it looks like some high quality secret to me.
Jeez.
It's a real active. Cool.
Cool.
All right. Anything else? That's it. Thanks.
I was going to ask, I mean, this is slightly like B trees. Is there any comparisons, like speed comparisons to B trees?
I mean, there is in the sense that you have it's a similar kind of concept. You have the try fan out. I think with B trees, what is it? Is it 4 typically? Can't remember. Yeah, it is. But I think it's similar. It's just that they basically took a much simpler idea and then they hacked to get the problems, the memory usage down.
So a comment from Tommy in Dallas Fort Worth. Pretty good C. I've seen much with the code. I've seen much worse. All right, cool. Thank you very much, Richard. All right. On to, and applause from Fort Worth. And now on to Doug Hoyte, our resident wizard.
So unmute the microphone and
You can. Screen share. Just go to the side here, click on the green, entire screen.
okay, great. All right. I can plug into here. Let me plug into here. Okay. Are we ready?
I don't think you're audible. I'm not seeing anything on your.
I did. Oh, wait. Yeah, I did. Was it?
Do you get a little? You should see a little.
Test, test, test. Oh, shit. Maybe my microphone.
Is there? I can't tell if the green thing's gone.
Test, test.
Oh, yeah, you
Test.
should be good.
Okay. All right. Are we ready? Okay, so my talk's Truncating Unicode. It's basically everyone's done it before. It came up and it's come up to me a bunch of times, and I've always thought there must be like a way to actually solve this thing once and for all. But I've always had like this niggling feeling that I'm probably corrupting data every time I need to truncate it, right? Every time ideally you shouldn't truncate as much as possible user data, but sometimes you inevitably do, right? So this talk is kind of like all the stuff I had to consider to learn about what this topic is, and also it's about unlike Richard's talk, which is substantially useful. There's a lot of crazy trivia that you probably will never have a chance to use. Oh, I'm sure there is probably at least one, just one. So there's a few times where you can few places where you can truncate, right? You can truncate before encoding, right? So that's you've got the high code point strings in Perl, right? And you can truncate them there, right? But the problem with that is that after you encode them, you really have no idea how many bytes that's going to take up, right? Because it depends on how many like high code point characters you have, quote unquote, and how and the normal form it's in, and all kinds of things, right? There's other problems with that, as we'll talk about in a second. The other thing you can do is just encode it into UTF-8 and then truncate it to the exact number of bytes you want, right? Oh, by the way, when I'm talking about truncation, it's usually about the number of bytes, right? Like, because, typically database fields and things like that work in bytes, network protocols works in bytes, things like that. Some will apply to Unicode code points and things too, but primarily bytes, right? The problem with truncating after encoding, like after you've got these sequence of UTF-8 bytes, is if you chop it up, you can do things like chop in the middle of a character and have like weird corrupted UTF-8 fragments trailing and things like that, right? And again, there's other issues I'll talk about in a second, even if you get that part right. So, yeah. By the way, that funny question marky kind of character thing you're seeing there, that's the output of that running that perl command.
Hate it.
Yeah, we've all seen it. It's basically what's happening there is that the perl actually is outputting an invalid UTF-8 sequence. It's outputting exactly 1 byte, as you can see, right? Like CC or CB or whatever it happens to be, right? But that's an invalid UTF-8 fragment, right? So when the terminal gets that, it says, oh, I can't output this in my UTF-8 terminal mode because that'll screw it up. So I'm going to convert it into a replacement character and display that, right? And yeah, the nice thing about that is that it becomes valid UTF-8, right? So it's quote unquote a good thing to do. But now you have these weirdo fragments of junk in your output, right? So stepping back a long time ago, all we had to worry about was ASCII, right? But I mean, actually, if we go back even further, there's this code called baudot code. And it's 5 bits, so that's 32 combinations, and it's originally for telegraph stuff.
Wasn't the original?
What's that?
It wasn't the original.
Yeah, well, no. But yeah, I mean, it's 5-bit codes have been used for a long time. Like Francis Bacon, forever ago, invented one for like a steganographic purpose, right? It's actually kind of neat. It was changing the fonts of particular characters in order to encode hidden messages, and which which characters do you change in the font and things like that. But yeah, it wasn't really for communication until 1870 when it was proposed for I think the French telegraph system. Okay, so if you have these character sets, they can only have 32 symbols in them or whatever. If you want some other language, what can you do about that, right? Like if you speak some other language, right? Can you encode other languages in this in the same alphabet? Yeah, of course you can, right? Like English, French, Spanish, all these other things use Latin, right? And there's other examples, Arabic. But it's ideally people would like to use their own language, right? Sorry. Yeah, you can, but it's not ideal. Switching the writing system altogether is even bigger proposal. Like try to get that past some insert country here that they should switch to ASCII and use that only. It's impossible, right? Well, not entirely, right? Because there's some examples of countries that have changed, right? Turkmenistan is just hilarious that they've had to change from Arabic to Latin, then just Cyrillic, and then back to Latin. But yeah, typically you don't want to force people to change, right? So now the problem really comes is that you have like these encoded sort of values, right? Like bits, or for example in Morse code the dits and dahs, and you want them to represent letters, right? So really the problem becomes if you have these same sequences of dits and dahs or bits, and they should represent multiple letters, right? Well, it's been a problem long before computers too, right? Even with the Morse code, they have the same sort of issues, right? Like for example, you can see the da da dit is P in English, and in Russian it's also like essentially the letter that sounds like P, right? And that's the reason for that is that of course Cyrillic is largely or it's has roots in Greek just like Latin does, right? However, there's there's a lot of problems, right? Like da v in Russian is the zh letter, right? So it doesn't actually quite work there, right? So now you've got sort of a conflicting problem, right? You have like these same sequences of bits that map to different letters, right? And that's really the crux of the problem, right? And yeah, these are just some interesting examples of reasons that people have shoehorned their own stuff into other character sets and things like that. Yeah, the first one is like it's sometimes called jokingly the Volapük encoding of Cyrillic, and it's basically it's used sometimes for like SMS providers because it's more expensive to send Cyrillic and UTF-8 because it takes up more bytes, so you can fit more into an SMS message. Yeah, and of course, yeah, you see the je letter there is those 3 ASCII characters, which I guess is probably more than UTF-8, but in any case. And then yeah, Arab easy is another kind of example, where because software support for like languages like Arabic and so on has been really bad for a long time. It's getting better now, but often they would have to type using ASCII, and it's a little bit hard to see because Arabic is always written in a cursive font. But like for example, you can see this 7 looking thing here. Of course, written right to left. That's like corresponding to the ASCII 7 and things like that. So it's just kind of sort of interesting, sort of way that people get around these sort of problems, right? So all these different languages, and we need to map them, right? Well, the obvious solution is we have these sort of code pages, right? We have these different mappings that we can swap out and do different things at different times, right? The classic example is like the Latin X, right? Or code pages, right? So you have Latin 1, which is partially backwards compatible with ASCII, but then you have the upper half of the code set, like the high, quote unquote high bytes, 128 to 255, and those map to some particular code pages of characters, right? And Latin 1 covers most of like the Western European languages, right? Except with the minor little niggle that if you're ever using Latin 1 or ISO 80591 on the internet on the web, you're actually using. Sorry, the poker tournament next door is acting up. Yeah, so Latin 1 actually refers on the internet now to 1252 because there was some unallocated space that Microsoft used for some other things, right? And of course, the rest of the world didn't want to be left out. So Japan, India, Korea, all had their their own types of code pages, right? But yeah, obviously, there's all kinds of problems with having different code pages that we'll talk about, right? But yeah, like now with Unicode and UTF-8, we never have to deal with code pages anymore, and it's completely obsolete and not used anywhere, right? Well, not so much. I don't know if you've ever accidentally catted a binary file to your screen and a Unix terminal and had the prompt screw up like that. Yeah, that's because the terminal. The way it works is that it wants to be able. There's a standard ISO 2022 that allows you to change the code page in use of the terminal, right? However, a lot of old terminals only support like 7-bit encodings. So yeah, usually what happens is it swaps it into these code pages where you send like 2 back-to-back 7-bit characters, and it turns it into like a normal or like some other code page, and the character is represented in there, right? So yeah, if you accidentally echo that sequence of 3 bytes there, like escape open paren 0, it switches you into some other code page mode, right? So here's the question: who all knows how to fix a terminal after this? Raise your hand. Okay, a few of you. Yeah. Other than close the terminal. Okay, so it's few. But obviously the answer is you memorize the ISO 2022 unescape sequence. You echo -D and then escape C. Or you can type reset if you have a crappy memory like that. That's fine. Whatever. No judgment. Oh, okay. Oh, okay. There's an option too. That's cool. Yeah.
It's the same. Yeah, but you can make sure.
So, getting back from this, enter the 1980s. Really, this little tiny specification was released, Unicode 88, and really ended up taking over all of our character sets, right? And arguably is a good thing. Most people think it is. In my opinion, like the real actual invention of Unicode, the thing that actually really made it successful, is that it decoupled what characters themselves as sort of abstract entities from like the actual bit sequences that are used to encode them, right? Like for example, if you look at like ASCII and Latin 1 and all these other ones, and going all the way back to like telegraph days, it always came down to the fact that this bit sequence or these dots and dashes in a row will correspond to this character, right? Whereas Unicode sort of abstracts it, right? It says, well, we're just going to enumerate all the characters and give them numbers, right? And then however you want to represent them is up to you, right? There'll be different Unicode transformation formats, right? Which is what UTF stands for, right? And basically whatever the use case that's appropriate is how we'll actually encode them in the bit level. But every character is going to have these abstract kind of numbers associated with them. And actually what they did is they assigned code points, these things called code points numbers. We'll talk about that in a second too. This is just an interesting thing I thought is kind of interesting, is that in the 19th century there's the Chinese telegraph system, which is like this big book of all the Chinese characters, and you could look it up and then get a number or those little 3-letter identifiers, and you could in different contexts transmit your Chinese characters based on those, right? Typically it would be digits over Morse code, but also letters and things like that in some contexts. Yeah, so it's kind of a play on the the Microsoft 64K is enough for anyone, whatever kind of thing. The original Unicode 88 spec said, it's basically we're just going to make it a little bit wider ASCII. It's going to be 16 bits at the end, right? Yeah, that didn't really work out. So ASCII is larger than that now. I mean, Unicode is larger than that now. But still, the Unicode I think had the right idea. Just it's actually changed quite a bit since Unicode 1. We're on Unicode 7. Unicode 8 is about to be released. There's been huge overhauls, tons of changes of it, but it's survived just because of it was designed to be extensible, right, and adaptable. So now that we've decided that every code point, sort of a character, should have their own its own number, right, and then the encodings are up to the context. The question was, what encoding should we actually end up using, right? The original standard-y kind of encoding, at least for internal representation of the programs and most files and so on, was UCS2, right? Which is essentially you just encode 2 bytes and encode the number, either in little endian or big endian format. That was one of the really annoying things about it. You had to worry about the endianness, and there was a special byte order marker and all kinds of nonsense. And you still have to do that with UTF-16, but that's UCS2, right? The standard 2 bytes original. And as you can see, it doesn't support the characters outside of the quote-unquote basic multilingual plane, right? Like, for example, the DVD signal, right? Like, what a tragedy that we can't represent the DVD signal as a character in our programs in UCS2. So UCS2 is completely deprecated, can't encode Unicode now, right? UTF-16 is the evolution of UCS2 that is essentially the same as UCS2, except it allows you to put these surrogate pairs, they're called, right? So you double it up and you have 2 UTF-16 surrogates next to each other to encode non-BMP characters, right? UTF-8 is, this probably pretty close to standard nowadays, and it's for most things, and it sort of has these surrogates at all levels, right? Like it starts with 1 for the ASCII range, and then goes up to 2, 3, and then 4, right? UTF-8 was actually originally specified for more than 4, but Unicode capped it such that currently, as of Unicode 7, you'll never have more than 4 to encode valid Unicode. Perl, interesting enough, uses UTF-8 internally, as you probably all know, and it actually allows you to put characters outside the specified Unicode range, right? That's useful for things like having sentinel values that will never actually be interpreted as Unicode and things like that, right? And will always break if you try to encode them as like a fail-safe, that kind of thing. So yeah, this is just like a little aside that I kind of think is a little interesting. Is one option for encoding of Unicode is a stateful mode, right? And it's really not. It didn't take off. It's not that used very much, but there's a few standards like SU, and that's sort of interesting in that just like our terminal, right? It can kind of change the window of which code points it's pointing at, right? So little characters sequences come in and they change what those like if you think about the Latin one way, it'd be like change from the Latin Western Latin to Cyrillic code page, whatever, right? And then you can change back if you have interspersed text. BOCU1, actually really interesting mode. It sort of reminds me of like image gradient filters, right? What you do is you store the first code point as a number in, I can't remember what it is. I think it's probably specified UTF 16 or something, and then, or maybe, actually I don't know. It's not important, but yeah, specify the number at first that you want to start with, like the first letter in your string, and after that you just store the differences, right? So if you have the string A, B, C, D, C, B, A, you can see it goes up by 1 every time, and it goes back down. And that compresses really well if you have, like, for example, things like gradients and images. And sort of the notion of this for Unicode is that, for a lot of text you're going to have like a ton of, like, say Latin, and then you're going to switch for like a quotation into Chinese or something like that. And that way you'll have like one big number that jumps you into the Chinese code range, and you'll have little numbers that jump around in the Chinese code range. And you'll go back down to Latin, one other big number, and then little numbers in Latin, right? Sort of a neat concept. But exactly. That's a huge downside of stateful encodings. They're not synchronizing, which we'll talk about really soon. That's a really good point. Yeah. So this is a kind of a fun word that originates from Japanese, mojibake. I don't know if I'm pronouncing that right. Actually, I have no idea. But it's basically whenever you load up a page and it's like looks all screwed up and there's the wrong characters and it just makes no sense. It's garbage. The Japanese, who've probably put up a lot more crap than we have, invented this word, and it's I just think it's a neat sort of new introduction to our lexicon for a problem that people experience that's caused by our technology. And yeah, speaking of the Japanese, that's also why we have like weirdo characters like pile of poo and things like that in the Unicode standard, right? It's because Unicode is kind of designed to be, like its name, is the one code, right? The code that unifies everything. And one of the things I wanted to do about that is make it so that you could unambiguously round trip between all the different character sets, right? So if you have a text in, like, say, the Japanese Shift.js encoding, you can convert that into Unicode and then convert that back to Shift.js, and there's no loss whatsoever, right? Which essentially means that for every character they have in Shift.js, there has to be a corresponding one in Unicode, right? So eventually, Unicode ends up being stuck with all these wacky things that some Japanese telco carrier invented because they wanted to emoticon it back and forth, right? So that's how pile of poo ever ended up in Unicode, if you were wondering. So yeah, so now we start to get into some of the problems of truncation itself, right? Like, so I think Tom Christensen came up with this phrase, the UTF-16 curse. And it's like, yeah, it's UTF-16 because it was adopted more before UTF-8, and a lot of languages jumped on it, like Java and also operating systems Windows. It really caused a lot of problems, and it's so embedded in everything that it's sort of like this curse that a lot of systems can't shake off, right? And yeah, here's like just a little demonstration of it at work, right? Like, so the default Python, unless you build it with some compile flag, for non-BMP characters, it doesn't even compute the length properly, right? Like, so you have that one code point, right? That mathematical symbol A, and if you print the len on that in Python, right? This is Python 2 or 3, by the way, I think. It'll print 2, right? Which is wrong, right? Perl does that properly because it used UTF-8, right? It skipped the whole UTF-16 internal encoding thing, so it doesn't have like these surrogate pairs, or rather, it dealt with the surrogate pairs a lot earlier because it had to with UTF-8. Yeah, Python has moved as of 3.3 to something a lot more like Perl, right? After decades of mocking the Perl's way of doing Unicode, it's come around to actually doing it this way, right? It kind of sort of is like Perl. It actually sometimes keeps UCS2 or UCS4 internally, but it also keeps UTF-8 as like a cache version. And yeah, here's another like example, like really gross example of UTF-16 that's embedded itself into everything we do. Like the JavaScript escape notation for non-BMP characters, you need to actually encode the UTF-16 surrogates, right? And it's really unfortunate this also impacts JSON, which is used everywhere, right? So if you want to embed
Just so everyone knows, Doug is rebooting at the moment and will be rejoining momentarily.
You guys like art?
Awesome.
There we go. No. Okay, sorry about that, everyone. Am I good now?
Your screen share is.
Huh?
Oh, there you go.
Is it? Okay. You see it there?
Yes. Oh, wait. No. Are you in mirror mode or are you doing? Okay. Maybe kill the screen share and start again. Did you stop it first?
I think. Camera.
Brief screenshot.
Oh shoot! I don't know.
Oh, we're all in there.
Maybe I should just use your computer.
Here.
The camera in my screen. No luck?
Switch to your.
Okay. Do you mind if I just use yours? All right.
Sure. Mute your microphone.
And your speaker. All right. Let's see if we can get this going here. Is this
Just a web page.
Sure. Okay. Where is it?
It's just here. It's my GitHub.
Okay. 1 second. Just double check. Dallas, can you see this? Do you see the screen share okay?
It was coming through. It's showing up on this.
Is it showing on mine? Okay.
Okay, good. Perfect. Well, actually, we can plug this in so you can see what you're doing. Cool. Come on, you little. Woo! Okay. Is this?
Truncate those strings.
Okay.
Okay. Okay. I think we got it going. That come up on your screen?
No.
No? Am I not screen sharing?
Oh.
Oh, my screen share stopped, okay.
Okay, there we go. Cool.
We're good?
What's wrong with there? Yeah. Okay, sorry about that, everyone. Yeah, it's a good idea. Right, so where were we? Okay, yeah. So yeah, the unfortunate thing is that UTF-16 rear ends head. Here's a problem with it in Node.js. It's also a problem in JSON. Is if you want to encode a character outside the basic multilingual plane, you have to encode the UTF-16 surrogates like that, which is pretty unfortunate. So anyway, UTF-8, really awesome format. The rumor has it that Ken Thompson invented it on a napkin one day in a restaurant.
With data searching.
Probably, I don't know.
Sorry,
Rob
Pike. Sorry, Rob Pike.
Yeah, that's an interesting anecdote. It was, got a lot of really nice properties. One of the things is that there's no null bytes unless you're actually trying to encode the null byte. And that's really useful for using it on Unix, for example, where null bytes have a special meaning. They terminate the string, right? Yeah,
it was designed for
True,
9.
exactly, yeah, and that's right. I didn't put it in the slides here, but yeah, I think they designed it for Plan 9. You're right. And for that reason, it was called the file system safe UCS transformation format initially, right? One of the reasons it took off is it's ASCII compatible. So if you have an ASCII document, it's already valid UTF-8. You don't need those crazy byte order marks we were talking about.
It's ASCII 7. It's ASCII 7 compatible, not full ASCII compatible.
Oh, okay, fair enough. True. And it's self-synchronizing, like we were talking about earlier, right? So it's if you jump to anywhere in the into a UTF-8 document, you can essentially fast forward through to the next UTF-8 encoded code point. But because the start byte of a UTF-8 sequence is special, right? It always starts with like the 0-bit or 1-1, I think, as it's most significant bits. One of the is that you really do need to check and validate it at your entry points when you're decoding it. You need to make sure that it doesn't encode these things, and it's called the overlong representation, right? Yeah, because the way that UTF-8 is specified, there's like some transformation operators where you can just apply and then get the code point that you're encoding. If you do it without ensuring that the code point is represented in the shortest possible form, then you have overlong UTF-8, and you can do things like sneak past validators and so on by having alternate representation of characters. Here's a really kind of interesting sort of thing semi-related to UTF-8. Again, it's for using amateur radio. It's this encoding called varicode, which is similar to UTF-8, except instead of having variable number of bytes, it actually encodes variable number of bits, right? It also has a special sequence of bits called the separator sequence. And in varicode's case, it's 2 zeros in a row, right? So just like UTF-8 has special start bytes that indicate like the separation between encoded code points, Veracode has this special 0,0 separator, right? It's also kind of neat because it's like Morse code, right? In fact, that's where it's inspired, right? In that really commonly used characters have shorter encodings, right? Like for example, the space character is just a single bit 1, right? And then followed by 0,0, of course, is separated from the next character. And less frequently used characters, like for example, I have like caret there has a much longer representation, right? And it's kind of one of the questions is like how do you generate these Veracode these codes that don't contain 0, 0, 1, 1 sequences? I just think it's really neat, so I had to throw it in here, and it has very little to do with Unicode. Although Veracode does actually support Unicode, so the sort of general name for these codes are called Fibonacci codes, right? And if you ever want to generate a code that doesn't have 0, 0 or 1, 1, which is the easier one to demonstrate here, that's why I've done it, is to follow this algorithm, right? So essentially you pick, you find the number you want to encode, and then you pick the largest Fibonacci number at or below that number, you set its bit, right? And then you subtract that from the total, and you keep on doing until you have no remaining value, right? It's at 0, right? And you can prove to yourself that it's you're never going to have 2 1s in a row with this by saying that like if you ever did have 2 1s in a row, then the Fibonacci number above it would be set, right? Because they sum to that one, meaning that the 2 below wouldn't be set, right? And then after you've done all those bits, you multiply together and sum them, sum of the Fibonacci numbers you've generated, and there's your you're back to your code point, right? So here you've got 1, 0, 0, 1, 0, 1, and if you ever want to generate ones that never have 3 1s in a row, there's n Bonaccis and Tribonaccis and Tetrabonaccis that you can use. So now getting back on onto the topic of truncation, right? So now that we've looked at all the ways that you encode these code points, right? And you got these surrogates and so on. But now there's another concept that Unicode has called combining characters, right? And essentially, what happens is that there's a lot of there's multiple ways you can write some characters, right? Like for example, if you have E with an accent, there's a special combining character called the accent character, what is it, like a acute accent modifier character that if you put immediately after the E, it'll modify it to put the accent on, right? It's so in other words, there's multiple representations of that one character, right? E with an accent, right? And one of the problems with truncating, of course, is that if you accidentally truncate, you can cut in the middle of these characters and their combining characters. In which case, like you could drop the accent, which could be a substantial corruption of the text, right? Like in English, we tend to think of it as not that big a deal, right? Like they're just like these extra little bits of annotation on characters, but some languages, the way they use Unicode are it's really critical that you not cut in the middle of their truncation characters, right? Thai is an interesting example, and it uses like modifiers to indicate vowels and things like that of letters, which can substantially change their meaning. So you wouldn't really want to say truncate and damage glyphs like that. Here's one interesting thing about Unicode 8. Since emoji is really taking steam, they've actually specified a bunch of modifiers to emoticons, right? One of them is that there's like a modifier about whether the system should show like a pictorial representation or a text representation of an emoticon. And this is like one of the more controversial / funny ones, is that there's like a skin color modifier combining character where I'm not sure who thought it was a good idea to pick which character or which skin color would be the base character, but
an old white guy.
Yeah, well, exactly. some old white guy, yeah. But yeah, no, they were doing really cool stuff with Unicode 8 and combining characters. And then no discussion of combining characters is complete without talking about the normalisation forms, right? So like I was saying, there's multiple representations for that E with an accent, right? And the normalized form compose, NFC, you look it up and see if there actually is a character with E accent, right? And of course there is, right? That was in Latin 1. So in that case, you replaced it with that single code point. Otherwise, you don't, right? Like if there was no such character, then you would leave it with a combining character, even a normal form composed. And normal form composed is actually a bit of a misnomer, and there's some cases where a normalization form composed will actually like increase it and not and decompose them. But yeah, then there's the explicit opposite, NFD, which makes sure that if it is possible to bust it up into combining characters. NFD is usually like a really horrible format to work with. It's not very good, but it has some, it has some processing applications. And yeah, like for some reason, the OS 10 file system, you do everything with exposed NFD, which causes a lot of problems for people. And then yeah, there's another special Unicode sort of combining character called the combining grapheme joiner. And yeah, it's got some really interesting applications for like doing weird stuff, and also some writing systems use it to like express interesting legacy characters and things like that, right? But it is generally something you don't worry about unless you have to, because you're trying to satisfy the Unicode test suite, which I'll talk about in a second. Another interesting thing is that its main purpose is to prevent composition, right? But it also like prevents the reordering of combining marks and so on, which sometimes matters. Here's like an interesting thing with combining characters is that you can see here some jokers put like a bajillion combining characters in that one thing, and this is how it ends up rendering it, right? Technically speaking, according to Unicode, there's no limit in the number of combining characters, right? Which leads to arguably bugs. I don't know if it's a bug or not, but it leads to issues like this where you have like some crazy character that goes off like that. There's one quote-unquote stream-safe recommendation, UAX15, that recommends that you limit it to 30. And yeah, according to people that have actually researched corpuses of code and so on, there's the largest they've ever found is the Tibetan language one that uses 8 combining marks on a base character. So you're probably safe if you limit it to 8 or 10, I would say. But yeah, so now we can start to like ask what is, like, we've been kind of talking about characters and code points and so on loosely, but like what does Unicode actually think of it is a character, right? What does Unicode define as a character? Bytes? No, definitely not, right? Like Unicode doesn't work on a low level like that. The code points, not so much, right? Because we have combining characters and all the rules around them and composition and so on. Unicode defines this notion called the extended grapheme cluster, right? And like you've probably seen if you've used \x in a regex, right? That matches the extended grapheme cluster, and it's specified by TR29 Unicode text segmentation, right? Which is essentially what we're trying to do. We're trying to segment our text when we truncate, right? We're trying to figure out the appropriate places to cut our text, right? It's called, extended, by the way, because they originally defined it as something else. It was like missing some stuff, and then had to deprecate that and put in this new one. But yeah, it's extended grapheme clusters are pretty much as close as you can get just looking at the Unicode stuff itself. If you don't know about your how your rendering images engine is actually going to display glyphs, right? Because it's slightly more complex. For example, with ligatures and so on, right? Your rendering engine can choose to merge together like F and I, right, to make one ligature. And so here's essentially the regex in that TR29 report. I can load up the web page, but this is pretty much what's in there, right? It says, if you want to match an external grapheme cluster, here's like this pretty simple little regexy thing, right? It's one of these terms, right? Which is pretty handy if you're writing implementation, especially the way I did it, which I'll show you in a second. And you can see that there's some special casing stuff going on there. I'll talk about that here. There's the Korean syllables, as you can see, Hangul syllable. And yeah, that's just because, Korean uses this pretty interesting construction for its Hangul script, where you can actually create the strokes and draw characters that weren't put into Unicode itself, right? So you can create essentially arbitrary characters, which is how their writing system works. And then there's also the regional indicators, which are essentially it's a response to, again, like those telcos that had special characters for, like, for example, the U.S. flag and so on, right? Well, guess what? Other countries complain, like, oh, why isn't there the Canadian flag? And they're like, well, we don't want to add one for every possible country. So what they ended up compromising on was adding 26 code points that encode the ISO 3166 country codes, right? So, in order to draw a Canadian flag in Unicode, you can use the regional indicator C, followed by regional indicator A, followed by regional indicator D, right? And that's defined as an extended graphing cluster, so it's one unit. Now we can kind of talk about what Unicode Truncate, my module, does, right? It takes UTF-8 as an input, and then it chops it off at a particular byte length, right? So you can put it in your database or whatever, right? That's, as I've said, is the goal, right? And then a nice feature that when I looked at all the other truncate modules on CPAN that they had too is if it does truncate, you add like a custom string at the end, right? Well, you can provide that string. By default, it's the ellipsis character, like the little dots. Then that just indicates that it was truncated, right? And then here's like the main design of it is that when it truncates, it always cuts at extended grapheme clusters, right? It never does any of those corruption things that we've talked about earlier, right? And it's also designed to be pretty efficient, right? So it does a single pass over the UTF-8 text, and it validates it as it goes, right? So the design is that you can get like a string from a user in like a web request, and do UTF-8 validation and truncate it to your limit in one step, right? And finally, it passes the segmentation test suite that I'll talk about that in a second. So yeah, just as a little bit of a detour, Inline C, you guys probably heard about it. It's really cool. It allows you to like write C programs in the middle of your Perl. I use that, and I guess I'll try to show the source code in a second. And I also wrote this module, Inline filters Ragel. I've talked about Ragel before, and I won't go into too much detail right now, but it's a code generator where you write in regex languages, and it generates C for you. And it's really cool. It's got a lot of features, and it's really neat. And my inline filters Ragel module, you can essentially say use inline C, and then you pass it the filters argument, and then it'll actually run the Ragel code for you, and that's inlined in your profile, and then the C, and then compile that, and then install that and load the shared object. Yeah, I also have this module inline LeanDist where it packages everything up for distribution and so on. So you just ship the generated C code, so the user doesn't need Ragel on their machine to use Unicode Truncate. So yeah, I just want to quickly show the code here if I can. Do I just create a tab?
In terminal?
Oh no, in the browser. It's probably easiest. Just connect to it. Yeah, so that big enough? Let's see here. How do we command plus?
Too big.
That's fine.
That's good. Okay, there we go. Yeah, it's regular. So yeah, we got use LeanDist, right? And we pass it the C data and then filters, and then here's our Ragel stuff, Ragel-G2. So that sets everything up for us, right? That's all we really need to create, like in XS and all the linking and stuff. And then yeah, now we can write our C/Ragel source code, right? So we have the data section, and there's the C section inside of that. And first we define this EGC scanner, extended grapheme cluster scanner, and that's Ragel, right? Those percent curly brace. That means shift into Ragel mode, and then inside here is going to be Ragel code. So essentially, I just define this little function, and it's just got some pointers and whatnot, and then I go into Ragel mode, right? And then essentially, I'm just defining my regex here, right? And now if you look at this regex is pretty much straight up copy paste of those regexes I showed you that are from the spec, right? So I just say, yeah, an RI sequence is one or more regional indicators, right? And these properties come from all uniprops, which I actually generate from the Unicode data off of the Unicode consortium website. And then I essentially have the main scanner here, which is, if you go and look at the regex on the Unicode website, it's essentially this. It just says, yeah, CRLF or one of these things, and then otherwise any UTF-8, right? and then I write out the data, and that's basically all there is. And yeah, so this is all just stuff handling the ellipsis and things like that. And then finally, I set the UTF-8 flag on, which indicates that it's been decoded to Perl essentially, and that it does contain valid UTF-8, and you can consider it to have higher order bytes because it has done the validation, as I said. And that's basically it. Yeah, the last little thing is that there's an in-place modification, right? So if you have a string, you don't actually have to copy it to truncate it, right? You just find the truncation, and then you just change the pointer in the Perl scalar to point to that. And I think that's the end of the module. And there's the docs. So it's.
And shift F to get out of full screen.
How do I switch to the other tab?
Or commit. Oh wait, no, commit shift F.
I see. Oh, wait.
And want to go back to the other tab?
I can't remember.
Was it the
Yeah.
first one?
Yeah.
Control 1. And 1.
Okay, cool. Yeah. Yeah. So the last thing. Yeah. So there's the Unicode test suite that I was talking about. Unicode is really awesome because they maintain like these really big data files and like test suites and so on. So if you ever do album implementation, you can actually test your stuff. The one that I was concerned with, of course, is the grapheme break test, and it's hundreds of these lines that are like this, right? They have little comments in them too, but they're basically this. It says, percent character means you can break here. X character means you. Divide character means you can break here. Times character means you can't, right? So in this case, it says, if you have a space, sure, you can break before that, right? But then you have a combining character after that, you can't cut in the middle of a space and a combining character, right? But then you have another space after that, you can cut in between that. And of course, you can cut at the beginning and the end, right? And that's pretty much my talk. So yeah, thanks for listening. And of course, yeah, Unicode Truncate is available on CPAN. And you saw my GitHub repo there. So thanks for listening. And if there's any questions, I'll try and answer them.
What was the original problem you were trying to solve?
Good question. So I had arbitrary user supplied input that's UTF-8, and unfortunately I couldn't send an error to the user if they exceeded a set length that I had, right? I needed to put it into a database, and the database field had like 50 bytes, say. So I had to either like completely fail and have a really bad user experience, or I could write, or I could truncate them and do a best effort inserting them into the database. And of course, I did the simple way at first, and thinking about this, I've done this many times before in the past, right? I just always had this niggling feeling they're probably corrupting user data, right? And then I decided to, look into it and see what it would actually take and see if there's anything else out there. There's another Unicode module called the Unicode GC string, grapheme cluster string, but the way it works, it's really, really slow to do simple things like this, right? Especially if you're looping over lots of user data all the time. That was my original use case, but I've essentially come up. I've had a whole bunch of other different applications that I've needed it for too. Like little headline summaries and things like that, where you only want to show a little bit of the text.
Well, how long has it been available?
I think I published it in December last year.
How much attention can you tell? How many times it's been downloaded?
I don't know about downloaded. I don't know if you can tell how many times it's been downloaded.
CPAN.
Yeah, I don't think CPAN tracks that, but I've had.
Tell on CPAN tracks it, so if people download there.
Oh, okay.
It can be tracked.
Okay. Anyway, RGBS wrote to me and said it's a pretty cool thing if he wants to use it. Unfortunately, he wrote to me before I had the inline Ragel distribution stuff working, so he was like, I can't install Ragel on this machine, so I can't use it. But, I should write to him and see if he can use it now, maybe.
Can you write us a Python notation? That'll cost you.
Yeah, well, actually, to be honest, some of the Ragel code probably could be repurposed. Yeah, like.
It's because like something like layer 10 API, we actually have to do exactly this.
Yeah, it comes up in all cases. The question was, can you please write me a Python implementation? So hint, hint, internet.
There was some applause
Oh, okay.
That's the story.
The answer to any question like that is how much you're prepared to pay.
Yeah, that's right.
Candy for our teams.
Yeah, you mentioned that, so currently the Unicode is limited to 4 bytes maximum. But that in Perl, for instance, you can go above that for sentinel characters. But what happens potentially in the future if, let's say, the consortium decides, hey, it's 6 bytes. Some of those sentinel characters aren't really sentinel anymore. And you've got code out in the wild that could potentially break.
Very good question. Yeah, the question was, if you pick a sentinel value in Perl that's not Unicode, what happens if Unicode extends it so that sentinel value is in Unicode? Really good question. Unicode has said that they won't raise it again, but they said that before and they were wrong.
640 days all you need.
But that's right. Yeah, it's a really good question. I mean, like Perl does support like a huge amount. I think you can have up to 8 bytes of Unicode 8, or sorry, UTF-8, which gives you like I don't know. It's really large. So you could use like the largest possible, I assume, right? But yeah, good question.
Go big or go home.
So have you seen Jonathan Worthington's blog post on introducing all this stuff to Perl 6? So Perl 6 now has strings that are grapheme based rather than code based.
Oh, nice. Neat. No, I haven't seen that. It's the comment was that Jonathan Worthington has a blog post about Perl 6 and how it uses grapheme cluster strings instead of code point strings. That's really cool.
That was just introduced like this week or last week or something like that.
Yeah, that's like the cutting edge of of string processing research, right? The obvious question that comes off of that is like, what happens if some joker has like that big character that has like a bajillion combining characters on it, right? Like how do you allocate storage and so on for that, things like that. But I'm sure they've thought that through.
Is limited to 8?
Possible, yeah. Yeah, it could be. I don't know. Yeah,
or it's all like, it all takes a UTF-8 strings.
Right. Yeah.
So it's already there. So.
True. Yeah, I mean, no, you're exactly right. Like in Perl, you can \x match one cluster, and it could be like 100 gigs of data in theory.
Somebody's code suggest that way, but that's good at the truncation.
Yeah, that's true.
It's fantastic.
Yeah.
So I mean, that just brings up a question though. Let's say you want to pre-allocate for a user 50 characters, how do you use extended graphemes for them to be able to enter in? I mean, how do you know how much actual real memory you're using?
Really good question. If you don't, yeah, I mean, like you could pessimistically assume that everyone is going to take 8, I guess, and then limit to 8 code points and limit to that, but that seems a little ridiculous. Don't know. Good question. Yeah, it's a really common problem because often you have like a web form and you are restricting it to like whatever the browser is. It's probably like you go length equals 10. That's 10 code points likely, right?
Does the browser is byte based or is it code based?
Good question. Does anyone know if you go length? Yeah, nice. Yeah, I thought it was code point too.
It's not byte. It's not grapheme.
Yeah, that's.
Yeah, but still, in the end, is you talk about your database is essentially are bytes.
Yeah, that's the other problem too. Yeah, it's like how to reconcile your database limitation with like your forms limitations that you provide the feedback right there to users too, right? I mean, you could on every key press you could UTF-8 encode the entire string and see if it exceeds your database limit, which is probably the best effort thing you can do.
You can't tell them, hey, yeah, it's only 20 characters. It's not actually correct.
Yeah, that's exactly right.
Usually bytes fast on YouTube.
Yeah, link them to the Unicode standards.
So if you're using a 7.
Okay, thanks a lot.
Cool.
Thank you.
Thank you very much to Richard and Doug for those talks. That was fantastic. We look forward to Mr. McDonald giving a talk next month. Anyone else want to do a talk? Because he's only promised us 20 minutes. Really?
I don't have a topic, but I'll figure it out.
You have 1 month.
Oh, that's plenty of
I'll only harass you a little bit.
After I do it here, I may see so that's my slot.
Well, great.
So it could be longer. But I got it.
Thank you all out there, and Texas is gone. Oh well. Signing off.